this talk is about cross-fertilization. It's about literature taking mathematics and using it to do really interesting things, but also mathematics discovering in literature really interesting, very hard problems that had not been solved, had not even been thought about. So it's really a cross-fertilization. And I want to begin the talk a little back in history with this man. This is about 1850, or no, a little earlier than that, maybe 1830s. And this is Leonhard Euler, who was a Swiss-born mathematician who worked most of his life in Russia, and part of his life in what at the time was known as Königsberg, which was part of East Prussia, which then became Germany, and now it's part of Russia, and the name is Kaliningrad. And he did a lot of work sort of pushing the boundaries of the mathematics at his time, and one of the questions he asked was related to the military. He actually got a lot of his money from military uses, and he thought of mathematics often in a military application sense, some of which were things like the stability of boats, but he asked himself one question which was more recreational and kind of fun. So he said, suppose you have 6 regiments of troops and 6 ranks of officers in each regiment. And so I have made the black troop with their different ranks of officers, and the pink troop, which is not very military, which is probably a good thing, the yellow troop, which is hard to see, and the green troop, and the red troop, and the blue troop. And he said, okay, now, you want them to form a parade when they go on their military parade, and you want in every row of the parade exactly 1 member of each troop. Well, that's not really so hard, right? It just means that I have to make sure that I have 1 color in every row. So do something like this, and I'm missing blue. And then start on the 2nd row and so on. He said, but no, 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 that's not enough. Also in each row, every rank at least once. So I can't have all the generals right at the front. I have to mix them up. So this blue 1 had better be a blue 2, and so on. And then he said, and still that's not enough. I want in every column 1 person from every regiment, and 1 person from every rank. So I can't have another black or another 1 in this column, right? So I could have a blue 3 and a yellow 2, and so on. And he said, can you do this? You've got 36 squares, you have to move them all around. And he didn't only ask the question for 6, he asked the question for any number. Could you do it for 2? Can you do it for 3? Can you do it for 4? And that's why I've given you the cards. So with the cards, with the normal deck of cards, you can do this just taking 3 suits in the end 2, 3. See if you can such a thing, a 3 by 3 square, so that you have a 1, 2, and 3 in every row and in every column, like Sudoku, and 3 different suits in every row and every column. And if you solve that, throw in your 4th suit. And if you solve that, there's 2 or 3 decks that have 5 and 6 suits lying around. So if you're really fast in this, you can go up to 5 and 6 suits. Like that. Okay. Well, and that's a really nice solution. Do you notice some patterns in there?
Yeah.
What patterns?
Diagonal.
Yeah, I've got the numbers going down to the right in diagonals, and if I wrapped it around, if it was a video game, right? So when I went off the right, I came in on the left, right? Then I would have the 2s going down to the right and the 1s going down to the right, and I have the colors coming down to the left. So that's actually pretty nice. Has anyone been working on 4?
Yeah. No.
Oh, okay.
Shall we?
Please do. Are you finding it much, much more difficult?
Yeah.
Yeah, totally. you can't do the diagonals, first off. If you even try it, it all goes wrong, right? Here's a solution for 4. And there is only, well, there's more than one solution, but there's only a couple solutions. The first thing to notice is I have a kind of diagonal thing. The 1s are going down, but then the 4s are going down in the other direction. It gets all mixed up, and the 2s are kind of going down, if I was on a video game screen, down to the left. Actually, that's probably like a video game screen from the 1980s. It's probably not a video game screen from the new millennium. Anyway. And the 3s are kind of all over, oh no, they're kind of going diagonally down to the right. The colors don't seem to really be doing much that's regular. And the reason is that 3 is prime and 4 is not. And you can't have that nice diagonal pattern unless you're actually a prime. Or odd. I think you can actually manage to do it for 15 and things like that. So, oil, yeah.
Sorry. So what's the rationale? Because if you look at your first row and your last row, they're reversed, and the second row and third row are reverses of one another. So it's a 1, 2, 3, 4, then a 4, 3, 2, 1 on your bottom row.
Oh yeah, well, and you've got these little subsquares here. See this 2 by 2 square and a 2 by 2? There's all patterns like that, and those subsquares come from the fact that 4 is a power of a prime. It's a power of 2, and that's why there's sort of those little mini 2 by 2s. And I think the reversal is actually another expression of that. So Euler looked for all of these things for various numbers, and he found 3, and he found 4, and he found one for 5, which is this one right here. And this one does have the diagonal patterns again. Blue colors going down to the left, numbers going down to the right. It works beautifully. 5 is easier than 4. And for 6, this is what he got. The best he could do.
Oh boy.
A couple of people had to stay home.
A couple of people had to stay home. Yeah, the military was underfunded in those days. Actually, that's not true. It was very well funded. And if you look at what we're going to have to, what we would have to put here, I'm missing a 1, and the color I'm missing is pink, but I've already used it. And here I'm missing a 2, and the color I need is yellow, and I've already used it. So you get stuck. And if you take these away and try and rearrange, you don't get any further. Lots of people try, right? And it's actually a really big problem because there's 36 different things you want to put down here, and you want to put them down in some order. And there's 36 factorial possible orders of 36 distinct items. And sure, I can do flips upside down, so it's not really 36 factorial, but it's still huge. And he couldn't get anything better than this. And so he said, you know what, I think you can't do it for 6. And then he tried 7, and he could do it, and he tried 8, and he could do it, and he tried 9, he could do it. 10, he couldn't do it, but that's really huge now. So I'm not sure that he tried very long. And he said, you know what, I think that they don't exist. 2 is easy. 6 he couldn't find. 10 he couldn't find. He says, I see there's a pattern there. They all differ by 4. And he called them Greco-Latin squares, but today we call them orthogonal Latin squares, a pair of orthogonal. Pair is, one is the numbers, one is the colors, that's the pair. And orthogonal is this condition, this Sudoku condition. So he said, you know what, I think they don't exist for 2, 6, 10, 14, 18, and so on. And this was early 1800s, and that he posed this conjecture, and people worked on it, but there was really no progress for a very, very, very long time. The first result after Euler, this is hundreds of years later, was Tarry, and he was a French mathematician and school teacher, and in 1900 he showed that 6 could not be done.